Ever wondered how computers untangle chaotic data? Like how they spot patterns when the information is noisy, incomplete, or just plain messy? Today, we're exploring a powerful technique called spectral clustering, and a groundbreaking method to measure uncertainty in those groupings. Think of it as giving algorithms a confidence score for their answers. Let's start with the basics. Spectral clustering is a mathematical tool that helps computers find hidden structures in data, even when those structures aren't obvious. Imagine trying to separate overlapping circles or scattered points. Traditional methods might fail, but spectral clustering uses linear algebra to reveal the underlying pattern. Here's the catch: real-world data is never perfect. Measurements drift, some points vanish, and noise creeps in. How do we know if the clusters the algorithm finds are reliable? That's where this research shines. The team treated uncertainty as a random process, like running a statistical simulation. They'd perturb the data slightly, adding noise, removing points, or shifting values, and track how clusters evolved. By repeating this process thousands of times, a technique called Monte Carlo approximation, they estimated the expected clustering. It's like asking, if the data had some wiggle room, what would the clusters probably look like? But here's the twist: comparing clusters isn't as simple as comparing two lists. There are two main approaches. The Lagrangian method tracks individual data points like particles, while the Eulerian approach looks at the big picture without needing every point to match. The Eulerian method is a game changer for incomplete or noisy data. Think of it as judging a crowd's mood without counting every person. The researchers introduced new ways to calculate expected clusters using random set theory, a framework for averaging uncertainty. They even developed a tailored metric for spectral clustering. And here's the breakthrough: their math proved that the order of handling infinite data points and infinite simulations doesn't matter. That's a huge win for reliability. So why does this matter? In fields like climate science, biology, or engineering, data is rarely flawless. This framework gives researchers a way to assess confidence in their results. It's like adding a trust level to every cluster the algorithm finds. Let's bring this to life with an example. Take the Wisconsin breast cancer dataset, 569 patient records with 30 measurements each. The researchers added random noise to simulate real-world errors and tested how well different clustering methods could distinguish malignant from benign tumors. They used PCA, a technique that simplifies complex data, to visualize the results. What did they find? Some methods held up better than others when data got messy, proving that no single approach works everywhere. The takeaway: when dealing with real-world data, uncertainty is inevitable. But with the right tools, we can turn that uncertainty into actionable insights. Whether you're analyzing medical scans, financial trends, or social networks, this research helps build more trustworthy models. Next time you see a machine learning result, remember, it's not just about finding patterns. It's about understanding how those patterns hold up when the world isn't perfect. Thanks for watching. If you want to explore how algorithms tackle real-world challenges, hit subscribe. And drop a comment: what's your favorite example of uncertainty in data?